Om Swastyastu, Assalamualaikum Warahmatullahi Wabarakatuh, Syallom and Namo Budaya, and hope to see you again. Now we go to the metallurgy in a modern alloy production. Let me introduce myself. I'm Imade Yudis Chrisantya. Have a name is 23055311063, and our lecturer is Professor Dr. Tjokorda Gde Tirta Nindhia, MT M Eng. And now we got the metallurgy with the code TM2301. I'm from Mechanical Engineering, Technical Faculty, and Udayana University. In this presentation, I got my main reference is from Metallurgy for the Non-Metallurgy Seccond Edition, edited by Arthur C. Reardon. Now we have a subchapter is effect of alloying on the solidification structure, melting furnace, molten metal processing, primary production casting, foundry casting, non-ferrous casting alloy, and powder metallurgy. As you know, modern alloy production, the manufacture of modern alloy is accomplished using a wide variety of melting, casting, and fabrication technique. The selection of the specific manufacturing process depends on the alloy system under consideration, the form of the product to be manufactured, the condition in which it must be provided, and the properties that it must be processed in order to be used effectively in the intended application. Now we go to the effect of alloying on the solidification. The solidification of alloying is a complex process, and it is most easily understood by examining how the solidification characteristics of alloy differ from those of pure metals. The solidification of pure metals: when a pure metal begins to melt, the solid liquid mixture stays at the melting point temperature until all of the solid has completely melted. The amount of the thermal energy needed to complete the transformation from solid to liquid is defined by latent heat of fusion of material. For the example, pure aluminum begins to melt at the temperature of 660 degrees Celsius and has a latent heat of fusion of 398 kJ/kg. If 1 kg of solid aluminum is heat to 660 degrees Celsius, then the addition of 30,098 kJ of the thermal energy will be required to completely melt the aluminum. Although heat might be continuously applied of the one after the material is entirely liquid, thus the temperature begins to rise again. As we can see in here, characteristic of the cooling curves, like the picture in here, the A is for pure metal with no foreign matter present, and the B is for pure metal with foreign matter present. The presence of impurities reduce the amount of supercooling because impurities in here produce a strong nucleating effect, but the melting point itself remains unaffected. And the C is the typical cooling curve for a solid solution alloy. Note, we can see that freezing from the L to S occur over a range of temperature. And next we go to the solidification. Okay, we go to the solidification structure. The solid liquid interface during the solidification normally exhibit one of the three types of crystal growth in the liquids, like planar, cellular, or dendritic growth. As so, in the type of the growth is controlled by manner in which heat is removed from the system. When the liquid ahead of the solid-liquid interface has a positive temperature gradient, heat is removed from the liquid by conduction through the growing solid. Because the temperature gradient is linear and uniformly perpendicular to the interface. A smooth interface is maintained and the growth is planar into the liquid. When there is a temperature inversion and the temperature decrease ahead of the solid-liquid interface, then either cellular or dendritic growth will occur. As we can see in here, ingot structure in the A, sketch of steel ingot showing chill zone, in here chill zone, columnar zone and acquisite zone. In the B is 1100 aluminum ingot we have without an acquisite zone in the center. And the C case 1000 aluminum coarse grain top we can see, and with grain definers added in the bottom. And next we go to the melting furnace. A wide variety of the furnace technologies are available for melting metals. In the steel making, for example, pig iron is produced in a blast furnace from iron ore, limestone, and chalk, because it contains excessively high level of silicon, manganese, carbon, and other elements. This liquid iron, together with scrap and fluxing agents, is then introduced into either a basic oxygen furnace or an electric arc furnace for further refining with oxygen. The objective is to reduce the silicon, manganese, and carbon to acceptably low levels into the resulting steel. Flow diagram of melting process used to produce steel. So you can see in here there is the process of the produce. In the furnace we have three types. The first is induction furnace. In the induction furnace are very advanced, are made in a many different sizes and are relatively simple in design and operation. As you know, this advantage have had decisive influence on the rapid increase of metal production by 3IM is like flexibility due to small batch size, fast change of program for different types of steel and alloy, easy operation, low losses of alloying element by oxidation, achievement of very close compositional tolerance, precise temperature control, low level of environmental pollution from dust output, removal of undesired trace element with high vapor pressure, and the last one is removal of dissolved gas, for example hydrogen and nitrogen. As we can see here, a cross-sectional view on the coral type induction furnace illustration for quadrant stirring action, which aids in producing a homogeneous melt. And the second is crucible furnace. Have a history been the most common types of furnace used, and records dating back to the dawn of the metals industry some 6,000 years ago indicate their use. There is an advantage use. Crucible furnace is a small, compact size and relative lower acquisition cost makes them economical. And the next is smaller, it's like and round. Furnace provide and maintain good even temperature profile. And the third is open crucible furnace, or even those with pivoting lid covers allow easy access for leading. And we can see here this is an electric bailout crucible furnace courtesy of the Morgan crucible. And the third, we go to the other furnace. Several other types of furnace have been developed by special application. For example, skull melting is the technique that is used when melting highly reactive metals. It's like titanium and zirconium that would otherwise attack the walls of the crucible lined with standard refractory materials. And the next, we go to the molten metal processing. Molten metal processing are and handled in various ways depending on the alloy and the melting practice that are used. Melting is a basic way of combining elements for the purpose of alloying, and the overall chemical composition of the molten alloy must be carefully controlled and processed before casting can take. Now we go to the fluxing of the metals, and often the first step in obtaining a clean melt. Fluxing is a term commonly used in foundries and melting departments that refers to the molten metal treatment from the additional of reactive chemicals, compound or inert gases. The various functions of the molten metal fluxing additives, either singly or combination, include removing inclusion impurities or dissolved gases from the melt, preventing excessive formation of solid phase inclusion, preventing and/or removing oxide buildup on furnace walls, and the last one is injection or distributing alloying constituents. In iron and steel making, for example, the function of the flux is twofold: to render the high melting refractory oxide impurities fusible and separable from the molten metals, to provide a medium with which the impurity element or compounds would combine in preference to the metals. And then next we go to the primary production casting. The primary production casting of metals normally involves either ingot casting of continuous casting of products such as a thread, sheet, wire or bar. Continuous casting offers certain benefits over static casting, but not all metals can be continuously cast. In the static ingot casting, several ingot casting processes have been designed and developed for downstream manufacturing process. The most common is straight ingot casting, where molten metal is poured into a vertical, open-ended mold. The mold is made of metal, usually cast iron, and is tapered along its length so that solidified metal can be easily withdrawn from it. As you can see the picture here, this is automatic stacker of ingot for foundries remelting, courtesy of the light metal edge. And here we can see cracking during forgings, rolling or extruding include like metal impurities, non-metal impurities, slag, dross and flux inclusion, invariant microstructure, segregation, surface crack and internal cooling crack. And the next is continuous casting process. Continuous casting may be defined as the continuous solidification and withdrawal of product from an open-ended shaping mold. The earliest method of continuous casting occurred in the 9000s with patents by Syallom for the manufacture of the lead pipes is in 9040 and by Legging in America for continuous casting of non-ferrous metal tube in 8043. And you can see in here schematic of vertical continuous casting process. Next we go to the foundry casting. Foundry use various methods to cast part with complex shapes interior surface. Molds are made in variety of ways so that the molten metal pour into the mold cavity result in a part with the shape and dimension of the finish from like the shape casting method can be divided into the three broad categories. Like there is casting with expandable mold such as sand, plaster, ceramic, and graphite molding. And the second is casting with reusable, it's like permanent molds. And the last one is casting with reusable permanent, but mold with the high pressure metal injection of the metal into the mold. It's like die casting, squeeze casting, and semi-solid processing. As we can see in two pictures in here is the schematic of the mold for a direct chill casting of aluminum ingot. And here is major component of the sand mold, and A is pattern assembly for cope and drag section, and the B is cross section of the mold with core. Next, we go to the non-ferrous casting alloy. In terms of tonnage, cast iron is the most common foundry alloy, constituting approximately a quarter of the worldwide production of casting. For example, the 40 census of the world casting production tabulate the total worldwide production of a casting in 2005 at 85,041,078 metric ton. Tonnage of the cast alloy in that years was distributed among the various alloy system as follows. Like in here we can see the gray has 40,007,088 and the total with all of this is 85 billion. The next we go to the aluminum casting alloy. Aluminum casting alloy are the most versatile of a common foundry alloys and generally have the highest castability rating. As casting materials, aluminum alloys have this favorable characteristic. It's like good fluidity for filling in section, low liquidus temperature relative to those required for many other metals, rapid heat transfer from the molten aluminum to the mold, providing shorter casting cycle, and the hydrogen in the only gas with appreciable solubility in aluminum and its alloy, and hydrogen solubility in aluminum can be readily controlled by processing method. Many aluminum alloy are relatively free from hot short cracking and tearing tendencies. Chemical stability good as such as cast surface finish with the true surface, that surface few or no blemish. And the copper casting alloy are unavailable as a sand continuous centrifugal permanent mold and some die casting. As we can see in here, they are generally similar to their broke counterparts, but have their own unique composite property characteristic. Like in here, a copper have UNS number is C10100 that has composition is over 99% Cu. And magnesium casting alloy of all types have found use in many commercial applications, especially where their lightness and rigidity are a major advantage, such as for chainsaw bodies, computer components, camera bodies, and certain portable tools and equipment. Magnesium alloy sand casting are used extensively in aerospace components. And next we go to the zinc casting alloy. Die casting is the process most often used for shaping zinc alloy. Sand casting, permanent mold casting, and continuous casting of the zinc alloys are also practiced, but account for the less than 10% of zinc casting tonnage. All the processes are based on the same family of alloy. And next you go to the last sub chapter is powder metallurgy. One of the more recent metallurgy development in the manufacture of modern alloys is the development of powder metallurgy, or we can say it's PM processing. Metal powder can be produced using a wide variety of mechanical methods as well as by chemical and electrochemical methods. The general type of atomization process encompasses a number of industrial and research methods. Industrial methods include like two-fluid atomization, where a liquid metal is broken up into droplets by impingement of high-pressure jets of gas, water, or oil, and centrifugal atomization, where liquid stream is dispersed into droplets by the centrifugal force of the rotating disc, cup, or electrode. And the vacuum or soluble gas atomization, where a molten metal is supersaturated with a gas that causes atomization of the metal in vacuum. And the last one is ultrasonic atomization, where a liquid metal film is agitated by ultrasonic vibration. In the water atomization, in terms of tonnage, water atomization is now the preeminent mode of atomization for metal, especially ferrous metal powder. The largest commercial application of water atomization is iron powder for press and sinter application, and approximately is like 90 to 70% of the world production of iron powder, which now total more than 6,100 metric tons of year is produced by water atomization. Water atomization is also used for the commercial production of copper alloy, nickel alloys, certain stainless steel and tool steel, and the soft magnetic powder for the pressing and sintering. As you can see in here, atomization process used in the industrial production of the metal powder. And thank you for watching my presentation. I hope you guys can get the good side about my presentation. And I close with Om Santi 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 Om. Assalamualaikum warahmatullahi wabarakatuh. Syallom. And I hope you always good. Bye bye.